Thank you. Okay, let me introduce you. Hello, everyone. Today this is another session for our random sample seminars, and today we have Aayush Karan presenting his seminars. Ayush is a PhD student at Harvard, advised by Professor Sitan Chen and Professor Junundu. So he works on probabilistic inference time scaling and reasoning for language modeling and for probabilistic modeling. And in particular today, he's going to present the reasoning with sampling. Your base model is smarter than you think. This is a work that received an oral presentation at ICLR and is going to be presented like in a few days in Brazil. And just to introduce the topic, so we all know about DeepSeek R1, OpenAI O1, all these reasoning models that made a huge splash at the beginning of 2025. And all these models are trained using RL algorithm or some form of reinforcement learning. And until recently, it was thought that the only way to obtain this kind of like capacities in language modeling was through reinforcement learning. And today, Ayush is going to present like a probabilistic method that shows how some of the capacities that we can achieve using a reinforcement learning algorithm can also be achieved using fundamental probabilistic inference methods, in particular like Bayesian algorithm grounded in probabilistic inference. So yeah, let's get started. When you're ready, Ayush.
Of course. Yeah. Thank you so much. Yeah. Thank you again for inviting me. Yeah, I really like the introduction. Great overview of what I'm going to talk about. But yeah, so my presentation is titled Reasoning with Sampling. Your base model is smarter than you think. And kind of the overarching message of this work and a few other works that I've been working on concurrently has been that I think there's a lot of value in trying to understand exactly what distribution your model is being trained on and what distribution you're sampling from at inference time, and like properly understanding what those two things are can kind of elucidate a lot of capabilities that have been emerging recently for all sorts of generative models. So you already kind of gave the brief overview of the reinforcement learning paradigm, but just to do a quick recap, for LLMs, reinforcement learning is often just a policy gradient with a verifiable reward signal on the base model. So popular methods are like GRPO and RLVR and its variants. And this has led to massive boosts in math coding and other STEM reasoning tasks, given the DeepSeek moment and the O1 series of models from OpenAI. So this has had a lot of success, but there are a few shortcomings that are suggestive of ways that we might want to find alternatives for reasoning. So the general downsides to post-training is that there's a lot of effort that goes into ensuring a verifiable reward signal. You need a curated data set to get reasoning capabilities to emerge. Training itself is susceptible to a lot of instabilities. There's the hyperparameters need to be carefully tuned for reinforcement learning to properly work. And in general, these companies are creating extensive rubrics trying to really push through a dense reward signal for general tasks that they're working on. On top of this, there's an issue of entropy collapse. The generation diversity at like multi-shot level reasoning collapses. So if you sample n times, there's actually a worse diversity relative to the base model for many of these post-training approaches. And this also leads to, multi-shot reasoning is also worse than the base model. And then finally, in general, post-trained models are also, they also tend to be uncalibrated and overconfident. There's something a little off about the marginals for next token probabilities with post-trained models. And these don't really seem to reflect natural language all that well. So this is kind of another issue with properties of the distribution of the post-trained model itself. So this is kind of an illustrative plot of this sort of entropy collapse phenomenon, which kind of inspires the approach that we take, where if you kind of sample n times, where here, this is taken from a different paper, Yue et al. 2025, where they track the accuracy over k samples of the base model relative to the post-trained model. And this post-train model is in red here. And as you can see, at a high enough number of samples, the base model's accuracy at k shot actually improves relative to the reinforcement learning model. So this kind of suggests that there might be some upper bound in capabilities where the reinforcement learning paradigm is shifting accuracy over to fewer shot performance. But in general, the sort of span of correctness for the base model is not too far off from the reinforcement learning model. And yeah, ideally what we want is that the reinforcement learning pass at k rate should be superseding the base model at all k, but this clearly doesn't happen, which is kind of pointing to this diversity collapse. So this kind of leads to a natural question: is RL just sharpening the base model distribution? Are we just sort of highlighting responses that the base model is already capable of producing, or is there anything fundamentally new that reinforcement learning is giving us? And this pass at k plot kind of gives this one suggestion. It suggests that the base model capabilities are bounding the post-training capabilities. And another way to see this, also taken from UA et al., and I'll have a plot that kind of reconfirms this later on, is that if you actually take the RL rollouts, you take the sequences that RL generates, and then you plot their likelihoods under the base model, it actually turns out that those likelihoods and those rollouts tend to have low perplexity and high confidence under the base model's distribution itself. So in this box plot here, this thing on the left is just sample rollouts from the base model itself, and their perplexities tend to be in this range. And then if you just post-train the model, take the RL rollouts, but then compute its perplexities under the original base model, these tend to occupy a lower perplexity region than the average responses from the base model itself. This is another massive hint that reinforcement learning is kind of producing rollouts the base model is already highly confident in, and that kind of, oh, sorry, yeah, go ahead.
So quick question, right? So how do you, so I actually buy the argument that this is RL in general should sharpen also, like how it is formulated, reverse scale and all that. The thing I was trying to understand is when you say sharpening versus whatever else that is, does that mean like increasing mass under a previously unexplored sample? I know, whatever the support is, right? Like, or again, redistributing it somehow. So I'm just trying to understand, like, if the base model has not really seen the data during pre-training versus, and then I take that condition, that situation, and then I try to look into what RL can do. I think that's kind of what I'm trying to understand. Because like the data sets that you were showing earlier, there's a good chance that they made their way into the pre-training.
Sure.
Right. So it's sort of like I'm just trying to understand if you looked into data sets that necessarily did not make it their way into like a synthetic thing that just didn't make its way into pre-training, and then sort of trying to understand if RL can in fact take that point that had zero support under the pre-training distribution and really shift mass to sort of a non-zero. Does that make sense? I mean, maybe I'm going ahead of myself right now, like, because you probably will cover this if you are going to. Just let me know if it's being covered, and I'll share.
No, that question makes a lot of sense. I guess there's two parts of it. One question you're asking is like, what do we ideally expect RL to do to the distribution that's not sharpening? And then the second is like, does this have to do with these data sets being seen during the pre-training distribution? Is that correct?
Yeah, those are the two questions. Yeah.
So for the first part, ideally, like the way reinforcement learning is typically presented is like you do want probability mass to be shifted towards low likelihood regions. Like you hope that even in GRPO, if you sample like several times, you want to kind of pick up on regions that are like lower likelihood under the base model distribution, but generate some positive reward signal. and then that signal gets propagated during post-training, and you redistribute mass to things that were low likelihood but have a high reward signal. So that's how you'd expect reinforcement learning to work in the ideal scenario. As for the dataset contamination and pre-training, I think it's a little tricky to disentangle the results in those settings, because yeah, we've all heard like maybe Quen has been trained on Math 500 and some of the other benchmarks during pre-training, in which case those are kind of somewhat already in distribution. It's kind of hard to say too much about like whether when it's seen during pre-training, how does that behavior qualitatively differ from data sets that you haven't seen during pre-training, just because we're not really like we'll eval on a bunch of data sets like outside of math, including like GPQA and human eval, which again, I think people to a lesser extent believe those are contaminated during pre-training, but again, I think it's just kind of hard to find an academic data set where like it genuinely hasn't seen it during, where we can confirm you haven't seen it during the pre-training distribution. But like ideally, like this argument is going under the assumption that the data sets that we're evaluating on are kind of like shielded under the pre-training process, and these are like fundamentally new problems. Like its train set may have been seen during training, right? So RL will train on the math, like Math 500 train set. So in some sense, the math task in and of itself is still somewhat in distribution, even during the reinforcement learning process. But
maybe just one final point I was trying to understand is like, because I think the 1 and 2 are very connected, right?
Sure.
So if I'm assuming that during pre-training the model was trained in a particular data set, right? Then all RL can do, in fact, is sharpen the distribution, right? Because definitely there was already significant mass if it went through pre-training, like a reasonable amount of mass on the right answer. So all you can, I mean, the RL behavior, I would argue, should be to sharpen, not to move it anywhere else, right? Otherwise, like self-consistency type things will just never work.
Sure.
So I guess I just want I just want to make sure that the two points are like somewhat entangled as well, right? It's very difficult to say that if the model is aware, and as you were showing in your plots, it already puts a significant amount of mass on the right answer. I mean, like a good, I think it's a decent hypothesis to say it saw it during the training. I'm not saying it's the only one, and if that is then true, the only right behavior for RL should be to sharpen that.
Sure. Yeah, I guess. Yeah, I see what you're saying. Yeah, so I guess the way I'd reframe that is like, it's kind of a matter of like, let's say you sample like 1,000 times for a given task under the base model. Like if you see the pass-it K rate kind of saturating at like 100%, which I think if you continue extending these plots, you kind of reach saturation at like you're able to answer these tasks with basically almost 100% accuracy given enough shots. I think that's like some evidence that points towards like, okay, it's seen like a proper role during the pre-training distribution. But in general, like the tasks you would stratify based on like what the pass-it K rates are. So like to define a hard evaluation data set, it would be like, you know, if you sample enough times, like what is the eventual like saturation point of its accuracy? And like for the harder data sets, that would be where accuracy kind of saturates much below like 100%. Those are like fundamentally difficult tasks. And you expect reinforcement learning to do something different in that scenario. Yes.
I mean, another example which we've been playing around a little bit with is like if I introduce like a made-up arithmetic, right, a synthetic arithmetic, where I use these alpha, beta, gamma symbols to mean addition, subtraction, division, multiplication. I can guarantee that pre-training has never seen this.
Sure.
Right. In that case, if I use RL, what we would expect and what we find is it does seem to learn this new thing.
Sure.
Right. And I think what I'm trying to understand if like there were some synthetic data sets that can be used to kind of do that delta, that this behavior, because like I think what would be very interesting, and maybe we should do this, is to
Great.
see if you can plot your plots that you're currently showing on the base model for the synthetic arithmetic or a made up, like, counterfactual type thing that we know the base model has never seen.
Sure. Yeah, that's a good point. Like a proper eval set that you can confirm hasn't been seen under the pre-training distribution. I think it's interesting to stratify them into like different categories of like, I've created this new synthetic task, probably hasn't seen it. Like, where does its like, what's the edge of capabilities where RL like provides something new versus just sharpens? Like, if you create a synthetic task and it's already like accurate at like multiple shots, then that's probably one of the tasks where like sharpening dominates. And then probably for tasks in like the 50% range, you might expect to see some kind of exploration give you like a signal boost. And then at the very low region, I think if you can't generate any like consistent signal, even with multiple samples, then you need something else to kind of solve those kinds of tasks.
Sounds good. Yeah. Thanks.
Yeah, of course. Yeah, I mean, yeah, I guess that sort of predicted the point that I was going to make, which was like the sharpening question again depends very tightly also on the training curriculum that you're running. Even in reinforcement learning, there are tasks of like progressive compositional difficulty. It's like another synthetic task where you can kind of create these functions that are atomic and kind of train the model to compose different atomic functions together. It's like a very specific synthetic task. And like things that people have seen are that reinforcement learning can eventually lead to some kind of compositionality behavior that's learned in the training curriculum. So there's basically just like different levels of operations that RL is doing. Like one is sharpening on what the base model already knows. And then there are ways of designing the training curriculum in practice to where you can go beyond the sharpening regime and start getting like compositional behavior from like unit atomic tasks that it sees during at train time. So yeah, sharpening is definitely not, we're not making the claim that reinforcement is only sharpening, but for the portion that is sharpening, I think those are, which tends to dominate a lot more in the academic settings. I'm not too sure about the industrial settings, but yeah, at least in the academic settings, sharpening is like a good portion. And so what we're proposing is a different approach to getting those, getting to that area of the distribution in a way that avoids some of the downfalls of post-training, which is like this collapse in generation diversity, like decreased passive K performance, things like that. And these are all within the base model's capabilities themselves. Yeah, like I said, sampling directly from the base model can achieve single-shot reasoning on par with RL in these settings where sharpening is dominating. And the other point is that this does not come at the expense of generation diversity or multi-shot performance. And this is also what we're proposing is a pure sampling approach where there's no training, verification, or data sets involved, which can be quite useful, especially in these non-verifiable domains. So the motivation for how to get around using reinforcement learning is to kind of think of what the distribution would look like that reinforcement learning is imposing on the base model. So if it induces a sharpening effect, you should independently be able to write down an explicit sharpening of the base model distribution and then sample from it directly. And so that's where these power distributions come in, where if you have a base distribution P, if you raise it to P to the alpha, where alpha is some number greater than 1, this has the natural effect of decreasing mass on lower likelihood regions and increasing mass in higher likelihood regions. And again, this isn't like, I made a point in response to that question where like true reasoning, which is what we want, should actually be in the regions of low likelihoods where the reward signal is higher. And so the point I'm trying to make here is that there's a significant amount of reasoning capability that's already within these like higher modes. And so having one way of accessing that region is a way of kind of taking the differential between reasoning that the base model is already quite good at versus reasoning that you actually want to tap into during like a proper post training. But power sampling will, of course, not be emphasizing the low likelihood, like high exploration, high reward regions of the base model. But yeah, this exponentiation is a natural way to sharpen a given distribution. It increases relative weight on high likelihood sequences and decreases weight on low likelihood sequences. This is kind of a natural description of a sharpening procedure on a distribution. And so one key point is that this is not the same as like token level low temperature sampling. So at low temperature sampling, you kind of sharpen the next token distribution at each point by introducing a temperature term into the softmax. If you actually write down the marginals for the low temperature sampling distribution versus the ideal distribution we'd want to target, which is this like full sequence level exponentiation, they're actually quite different in a subtly but important way. So in this sort of first equation, the induced distribution kind of takes a sum over all future paths. So let's say we're adjusting the distribution at time t. So this is like the marginal that we care about. Then low temperature distribution is first summing over all these future paths of this base model distribution, and then it takes the exponent to the power alpha, and that's what determines the relative weights on each of the tokens xt. Meanwhile, what the power distribution is doing is it's first taking each future path, it's exponentiating them to this power alpha, and then it's taking the average over them. So there's a important way in which these two things are different, where this averaging all future paths before sharpening, what this tends to do is emphasize tokens that have many low likelihood future paths instead of few high likelihood ones. Because on average, just because you're summing over all these future paths, there's no distinction between the quality of these future completions. If you have many low likelihood future completions, the mass is the same as something as like one future completion with that entire mass altogether. So on average, there's no distinction between these two things. So it is possible to sample tokens that traps you in a low likelihood future completion. But power sampling, on the other hand, like doing a proper full sequence distributional sampling, this sharpens the future paths and then averages. So this actually downweights low likelihood futures and then samples tokens. It prefers sampling tokens that have high likelihood future completions as opposed to like many different low likelihood ones. And so like there's this kind of planning in this that's kind of inherent to this kind of sampling approach that would suggest that these power distributions are better for reasoning even over these like low temperature sampling approaches, where there's like this inductive bias for planning where you're avoiding sampling these tokens that are going to trap your future completion in some low likelihood region. And so this requires, some increase in inference time compute to actually conduct this planning when you're sampling, but you are kind of forward looking in choosing the right token and in its influence on the future completion. And these sampling tokens are work that we've done in the past before. So I'll just briefly plug a paper where we kind of showed that there exist these critical windows in LLMs where essentially a few tokens are fully determinant of the final accuracy of the language model. So there's like a pretty sharp window where if the model samples the wrong token, it kind of completely determines the future output, regardless of the future tokens that are actually generated. These are these things called pivotal tokens that the 5.4 team also found when they were training that model. And they found that, there's very sharp windows where the token that you actually sample from is very important and is indicative of the final completion accuracy way before you actually continue the rest of the rollout. So this is another point in service of the argument that we should be sampling tokens with a future look ahead in mind. So these power distributions, hopefully by now, are well-motivated targets. So the next question is how we actually should sample from them. Because in general, a p to the alpha distribution is intractable to actually sample from. It's not a normalized distribution. Like the sum of all possibilities doesn't sum to 1. And like in practice, we're not going to be summing over all these future paths to actually do this normalization, because there's exponentially many of them, given that scales with the length of the sequence. This is a computationally hard problem, and will sort of take use of a long litany of work from the classical sampling literature, which are these Metropolis-Hastings algorithms, which specifically target approximate sampling from unnormalized distributions. So the general way that this works is that you build a chain of samples that eventually converges to a sample from the distribution you want to target from. So you have a proposal distribution, which in our case is going to be the base model's LLM. And we use that base model to sort of iteratively generate new candidate samples, which are just rollouts given a prompt. And then using this proposal distribution, we have this new candidate sample, and we accept or reject that new sample with this probability that I have on screen here. And this is basically a function of the probability of this new sample under both the target distribution and the proposal distribution that you're using to sample from. And the way that this is constructed is so that it perfectly kind of balances out the distribution induced by the proposal, and kind of only leaves out the target distribution's likelihood in that sense. So that's kind of this ratio that sort of forces the eventual candidate to converge to a sample from this target distribution, which in our case is the powered distribution. And so, like, what we're doing, like, physically is we have to define a proposal distribution. Like, how do we mutate a current candidate X into a new sample X prime, and then figure out whether or not we need to accept or reject it. So what we're doing is we take an arbitrary index in the middle, some random portion of the sequence that we've generated, and then we resample the suffix. So the original has its one completion, and then we resample starting from index t, and we have a new suffix at the end. We calculate their p to the alpha weights, which we can do because we have access to the base model, and then we can just directly compute the temperature scaled version over the entire sequence. With some probability, we'll accept or reject this new candidate sequence, and then we kind of repeat this process over and over again. And Metropolis-Hastings guarantees us theoretically that this will eventually converge to a sample from p to the alpha, the normalized distribution. And so this is just a brief animation again of what's going on, if that wasn't too clear, but there's some sort of original rollout that gets generated. We start from a random intermediary index, resample that, calculate the relative probabilities, and then probabilistically accept or reject a new sample. And so one issue with this is that if you kind of run this, this is called an MCMC algorithm as well. Metropolis-Hastings is one of several different MCMC algorithms, which are Markov chain Monte Carlo sampling algorithms. But running this process over the full length of the distribution can also, even though we're theoretically guaranteed to converge to a sample from our target distribution, the convergence rate can be exponential. So we also do need to be careful about how exactly we approach getting to this full sequence target distribution. And so this is more of like an empirical trick that is motivated by like theoretical observations about convergence. But what we essentially end up doing is we construct a chain of distributions that anneal to the full sequence power distribution that we want to target from. All this means is that we kind of do this blockwise, where we take a certain intermediary sequence length and target sampling from the power distribution up to that block length. And then we progressively increase that block length using samples that are initialized from the previous distribution. So this actually, in practice, ends up cutting down the convergence time, at least to a stable accuracy by quite a bit. And the number of tokens that are expended in this scales linearly with the number of MCMC steps, and then is proportional to t squared over b, where t is the sequence length. So if you choose the block size to be a constant fraction of the full sequence length, then the inference time scaling is linear in both the number of MCMC steps you choose as well as the sequence length itself. So the inference time compute is not that bad.
Hey, one quick question. So you have a single chain here?
Sorry, single chain as in single sequence of distributions?
Yeah.
Yes, like there's we're taking one sample at a time. It's not like multiple parallel samples going together. There's one sample at a time, and then that gets mutated up to block size B, and then that continues to progress onwards.
Okay. Okay. And are you gonna talk a little bit about the mixing later, or I'm just trying to understand, like, if I to be honest, let me ask this question at the very end, because you might be covering this thing. I just want to understand what's the mixing behavior, and do you construct it in a way that it does asymptotically get to the distribution. I guess what I'm trying to understand is, do you have multiple samples with different alphas running in parallel, or do you have like a single chain with a fixed alpha? Does that make sense?
Yeah, that makes sense. Yeah, so okay, yeah, so I will like somewhat cover this later on, but I'll just mention this.
I'll wait until that.
No worries. Yeah, I can just cover this now because it's a good point. So I think what you're referring to with multiple different alphas is this like parallel tempering style MCMC, which is like another approach to kind of trying to decrease the mixing time to getting to your target distribution. So we're not doing any sort of parallel tempering here. Also, just because I think it's like you don't need to do parallel tempering. I think the single chain. So defining when mixing happens empirically is a little difficult to do. It's hard to tell, like, after you've run a bunch of samples. Like, the only way to confirm at a certain point whether your sample is like reasonably under your mixing distribution is just to go ahead and do the full normalization and confirm whether or not that sample is like over multiple samples like matching the normalization weight. So verifying that you're mixing is also quite difficult. So like the proxy for that is kind of understanding like
acceptance of the
sorry
your ratio of acceptance and all those sort of like is that something you're tracking as well? I mean, I'm assuming you're tracking.
Yeah, that's one other way. So I was gonna say like the way that we're tracking it is just like ultimately all we care about is like performance on downstream like benchmarks. And so again, what we're looking at is when does accuracy stabilize if we scale this long enough. And so we're already finding that like the number of MCMC steps can be quite low and the accuracy basically stabilizes like quite quickly. So there's actually just no benefit of quote unquote further mixing beyond that point. But I will mention that it is difficult to distinguish whether that's confirmation that we are mixing at a low number of MCMC steps, or whether accuracy just stabilizes at an intermediate, like annealed distribution, and there's no real difference between the power distribution and what we're sampling from if it's not mixing. We are also tracking the acceptance rates. So, like, again, this is all heuristics. There's like nothing provable in the literature about this, but in general, from classical MCMC literature, like you want your acceptance rate to be around 67%, like somewhere in the 60 to 80% range, where you can like somewhat be appreciable of mixing happening. And we are finding that our acceptance rates ends up being like quite high towards the end of this process. They're in that like 60 to 80% range. So that kind of gives us somewhat of a signal that like when accuracy is stabilizing, this is also corresponding to like the mixing that we care about being terminated.
Thanks.
Yeah. Okay, yeah, I'll skip this slide. It's just an explanation of the algorithm that we're running. But again, this is kind of the full schematic of this like iterative autoregressive like MCMC style technique that we're doing, where we're building this block by block, resampling suffixes based on their likelihoods, accepting or rejecting, and then continuing to build the sequence onwards and onwards. And so, yeah, I mean, like algorithmically, this isn't like this isn't too different from like a following process where you kind of have an existing sample, you're mutating it in like specifically good ways, and then you're kind of using the model's likelihood as a verification signal to kind of improve the quality of the response. So it is kind of in spirit what this algorithm is doing, even though it's framed as like a MCMC approach. So I guess I could briefly talk about the results, which are just that power sampling, which is our approach, nearly matches, if not outperforms, GRPO across various domains and base models. And then these are all these domains that are kind of academically relevant that are kind of standard in the literature. So that kind of is dictating our choice of what we're evaluating on. So the things that we're evaluating on are Math 500, Human Eval, GPQA, and Alpaca Eval. So like kind of like to the point of the pre-training contamination question beforehand. So Math 500 is one of those tasks where the base model Quen, I think, is highly suspected to have saturated on it. We have results on Phi as well, but I think that's less controversial as to whether Math contaminates the pre-training data set. And we also see boost there, but definitely for Human Eval and GPQA, their Passat K scaling is not really nowhere near like 100% accuracy if you sample enough time. So these are like fundamentally like not super difficult, but not super easy tasks either, where the base model gets like an appreciable performance on them. So this is still like a regime where it's like, I don't think you can claim immediately that the pre-training distribution has seen the GPQA task just because if you sample enough times, it's still not getting perfect accuracy on GPQA. Like you're not generating a rollout that will always solve a problem given enough resources. So this is one of those tasks where I will say that like the sharpening regime still dominates. And I'd say like more so than pre-training contamination, the thing that really determines in reinforcement learning what your like whether the sharpening regime dominates or if you're actually doing fundamental exploration is actually just in the training curriculum that you're using RL for. And so like if you're able to structure a training curriculum that progressively makes problems difficult and kind of like very like slightly starts shifting mass towards like problems that you wouldn't really be able to solve under the base model, but that require like chain together different skills that the base model is confident on, then you can like build a compositional depth that way where you get beyond the sharpening regime. But like for these tasks, that's not the case for the models and RL training setups that are available. So GPQA is kind of and Human Eval to an extent are kind of exempt from the criticisms about like pre-training contamination that Math has from Quen. And they're also out of domain tasks as well. So we are doing reinforcement learning on Math specifically. So yeah, and given that sort of pretext, basically we're just seeing that targeting this power distribution is performing quite similarly to how reinforcement learning would perform. So on Math, we're not reaching the full accuracy that GRPO gets, but on out-of-domain tasks, we're basically either matching, like in GPQA, or for Human Eval, we're actually going beyond the performance that GRPO is able to achieve. And then these are reasoning tasks with a verifiable signal. We also try an unverifiable domain, which is Alpaca Eval. And I mean, the base model is not terribly good at these sort of free-form style responses, which is just like this general helpfulness task. But again, we are able to go beyond what GRPO is able to get on top of the base model as well. So this is single shot reasoning, this performance at one shot, and then as kind of a table, we try on Quen, but we also try on Phi 3.5, and we also see like similar boosts. We see a similar boost in power sampling on Math, Human Eval, GPQA. The boosts are quite prominent relative, especially to GRPO. And so the second point that I'm making is that power sampling is actually defining a better reasoning distribution to sample from altogether. So like one question might just be like, what's the point of running power sampling if reinforcement already works great for one-shot sampling? Which is a good point. Like you're incurring inference cost where RL only infers a training cost. But there's actually something quite interesting about the like P to the alpha distribution when you like targetly sample from it, which is that in general it seems to have like a richer reasoning distribution than the distribution that's induced by reinforcement learning during post-training. And so this is this diversity collapse issue where your passive K performance decays after you run RL. And so this is kind of, I'll come back to this, but this is kind of like the plot from earlier where you're seeing that your passive K accuracy is actually decaying relative to the base model. And you're not actually saturating at 100% with enough K. And so this base model is here in blue. There's a crossover point where the base model's passive K accuracy overcomes what post-training is able to get you. And then our distribution, this like P to the alpha distribution that we're sampling from, is kind of giving you the exact behavior that you would want from like a stronger reasoning distribution, which is that at every single K, we're superseding what the base model's like passive K accuracy is. And then eventually it converges because again, like we are drawing, like our base model is our proposal distribution. So we are sampling directly from the base model, just transforming the distribution. So it eventually does converge. But like ideally, when you're learning something new with reinforcement learning, there will be separation between the base model's passive K curve and the ideal like reasoning curve that you would want. But this is like a nice middle ground where we get the sort of best of both worlds at an inference cost, which is that we have much higher single shot accuracy, which is great. And then this translates to better accuracy, multi-shot reasoning. Yeah.
Yeah, it's me again. Sorry, I've been interrupting you continuously.
No worries, no worries.
This is very interesting. So 2 points. One, I just want to make sure that like the pre-training part, right, the contamination, I don't think that's a criticism. That's just, I think that's like, at least in my, the reason I brought it up is because I think I want to characterize like what is sharpening versus like moving mass actually means. And
Sure.
So that's just that, right? The second thing, which I guess like this plot is bringing up, which is kind of very interesting, is because you mentioned, I mean, you know, the equations you showed for how nucleus sampling works versus how power sampling works. Given that GRPO actually uses, you know, a temperature-based sampling, right? Is that the underlying reason for the collapse? So where I'm getting to is, did any chance you ran any experiments where within the GRPO sampling loop, you sampled using, you know, your method?
I see.
Right?
Yeah.
That, I mean, it is true that GRPO leads to collapse, but it's also like not very clear why should it, right? Like, I mean, if I'm sampling through what you're showing me here, right? So that point really made sense to me that you said that, you know, how if you are sharpening on top of low likelihood samples, yes, you will, that could at least like as a hypothesis be the reason why collapse actually happens, or at least one of the contributing factors. Oh, do you have any thoughts on that?
Yeah, that's a good point. We have not run experiments on this, but that has been something in mind of like, what if you ran power sampling as the like inference distribution during GRPO? I think it's my understanding that the diversity collapse from GRPO has to do more with the way that the objective is set up, more so than what your inference sampling distribution is. I think because I mean, like people usually make this argument about this like mode seeking versus mode covering approach, where like the reverse KL divergence for GRPO is kind of set up in a way that is like mode seeking, and so you tend to like when you sample like a finite amount during GRPO, like you tend to cover the mode that you're sampling from, which is like good for single shot reasoning. I think it's like a matter of like what happens to the mass of like sequences that you don't see during sampling time And so the argument would be there that like GRPO aggressively fits to the sort of distribution of samples that you see at sampling time. But if you don't like, if there's a like diverse amount of rollouts that you're not seeing that aren't generating reward signal, like the argument there would just be that like the way the objective is set up for GRPO itself, it like shifts mass to the regions that it's like more confident in, which is this like mode collapse issue.
I agree with you that like I mean the way I mean GRPO or any most RLs are some kind of reverse scale, right? But that distribution that you actually end up sampling from, I think the sampler itself has to make sure that the samples are coming from the right mode. I guess what I'm trying to say here is that if I want to sample from the dominant modes, right, then wouldn't this power sampling, I mean, your method essentially, wouldn't that be more truthful? Because I mean, like, I guess what I'm trying to get to is there's nothing inherently wrong with mode seeking if that is the right mode you want to sharpen around.
Sure.
Right. But the question is this nuclear sampling like inherently flawed in some sense to never actually give you samples from the, I mean, you know, is it a good, like, is it really getting to that mode? Because, yeah, I get, yeah, that's the.
Yeah, that's a good question. I think, again, my understanding is more so that like this mode collapse issue is like a finite sampling and optimizing issue rather than like the actual distribution you're sampling from at the time. But that being said, I think like given that you're expending this inference time compute to generate samples from a richer distribution, I think it is possible that like you could make the argument. Again, it's hard to define like what modes exactly are in this situation, but I think you could reasonably argue, like you'd have to see the results at the end, but if you're doing power sampling during GRPO, you're getting signal from like a richer distribution than like what you'd typically be getting with like this nuclear like low temperature sampling approach. And so that might, like if you have a better expanse of responses that you see during GRPO, I think you could argue that would fit, that would lead to a less degradation in the passed K accuracy. But like that's sort of hypothesizing. We'd have to run the experiments to actually confirm that. But I think like in general,
can we collapse? So GRPO collapses, but can we collapse the power distribution? Well, the mode formed by the power sampling. I think that's kind of where I'm going with this.
Right. Yeah, I think you could. Yeah, I think that's a good point. I think you can collapse to the power distribution. Like I don't think you'd get strictly worse performance by doing power sampling during GRPO. Like I think you could only expect your passed K rate to boost to boost what GRPO is able to get. I think the point that I'm not 100% swayed one way or the other is like what does GRPO on the power distribution look like compared to just sampling from the power distribution relative to the base model itself. I think what I'd expect to happen is that like the passed K performance might like slightly increase at like lower K, but I think like there still might be a gap between the like higher K values. I think that part
I agree with you. I mean, to me, this is some kind of I mean, if you do that, that's an amortization, right?
Right.
I'm saying that I can take the cost of running the slightly more expensive sampling during the inner loop of GRPO.
Right.
But then it should like it would only close some gap. It wouldn't fully cover it. If it's a true amortization. In some cases, it should fully cover it, but yeah, it shouldn't lead to the same performance overall.
Right. But yeah. I think you can do at least a little better than what GRPO is able to do. I think another point to also keep in mind is like this also comes back to the earlier question about like, are you trying to do sharpening better or are you trying to do exploration better? And so I think you should also keep that in mind when trying to apply this. So like, as I mentioned, the power distribution itself is like suppressing low likelihood regions in favor of high likelihood regions. There's less mode collapse in total in terms of like the number of high likelihood regions. So if sharpening is what you want to do, then like this makes sense. But again, if like exploration is the thing that you care about, then I think that there isn't really a difference between like power sampling or low temperature sampling. In fact, you should probably do high temperature sampling if exploration is what you care about. And that would sort of correspond. That's kind of another direction that we're interested in, which is like right now we're sampling from P to the alpha, where alpha is like greater than 1. If we set alpha less than 1, that's also like higher fidelity, high temperature sampling, which may or may not be better for exploration under the base model. So that's kind of I think that's what you'd care for exploration.
That's really interesting because, again, I mean, this is going in a completely different direction. But essentially, if alpha is a learned parameter during the inner loop of GRPO, I think that will be an interesting thing. Essentially, like an adaptive GRPO. So, like, if your advantage is net 0, you essentially move it up or down. Well, you move it down because you want to find. I mean, if it's 0 because there's no true answer, or you move it up if you know it is correct anyway.
Right. Yeah, alpha is a learnable parameter, could be interesting. You'd need some kind of feedback on. I mean, you can always get feedback.
The advantage is a feedback, right? If your net advantage for a batch is repeatedly going like is 0, right? And you might want to explore more.
Right. Yeah, exactly. Like you'd use the like variance in your reward signal from the batch and GRPO as like as something that dictates like how good your alpha parameter is at that point. Like if you are not sampling anything with reward signal, then you'd probably want to go to a lower alpha to get better exploration. But if you have a good mix, then you'd want to increase alpha, and like it's like an exploration exploitation trade-off, like during GRPO, where you can adaptively exploit like alpha parameters that give you a high reward signal. But when that doesn't work, then you need to revert to high temperature sampling. Something heuristic might be good enough where like you don't really like set alpha to be learnable, but you kind of like take one batch and like based on the variance, either take alpha to be 4 or like a reasonably high enough number, or you just take alpha to be like less than 1 if you're not getting any variance. I think that would probably like in effect do what you're talking about.
Yeah. This is great, man. I think this work is amazing. Thanks
Sure.
Yeah.
Of course, yeah. Yeah. I mean, yeah, I could quickly sort of just continue showing the results. Yeah, I mean, this is the sort of math performance. GPQA is similar. Human eval is also similar. The point I was trying to make with these plots is kind of similar to this, like the rollouts from post training are in like high likelihood regions. This is kind of also a point towards the diversity as well. But like if you look at the rollouts for GRPO and just look at like what that histogram looks like under a metric like the average log likelihood over the sequence or the average confidence over the sequence, like you can also already see that like it's very narrowly peaked, even though it's at very high likelihood under the like base model span. It's like under a high likelihood region. And so if you want to visualize like where is the distribution that we're sampling from, it's like some kind of like wider but like higher likelihood like region that's not exactly like that's definitely better than the base model, but it's not as like collapsed as this GRPO distribution either. And so this is true for both log likelihood and confidence, that we still have a higher span. We're not getting to as high likelihood that GRPO is getting, but like again, likelihood isn't our target. It's sort of overall accuracy. So it's maybe not the 100% like best fidelity conversion, but to some extent, like this is kind of doing in effect what we want power sampling to do, which is to avoid this like narrow peak at a single likelihood and actually have a span over responses, but still like on average shift mass towards the higher likelihood regions under the base model itself. This is kind of like a plot illustrating that that's like in effect what we're trying to force to happen with power sampling, and actually we can see hints of that empirically. And then yeah, this is the sort of like last point I wanted to make about like mixing time, where instead of mixing time, we're kind of just looking at like when does accuracy stabilize. I cut off the plot at 10 MCMC steps because it stabilizes after 10 MCMC steps, but like you can kind of think of this as like at least from the range of 0 to 10 where you'd expect mixing to happen, you can kind of see this like gradual increase in reasoning performance. It's not like 100% perfect, but like in general, like starting from 0 to 10 over like multiple rounds, you can see that like on average the reasoning performance is shifting up as you increase the MCMC steps, and that's sort of what constitutes the full boost. So there's like an interesting test time scaling perspective on this, where you can like, to a degree of gradation, by controlling the number of MCMC steps, like control the accuracy boost at the expense of like inference costing. So yeah, the takeaways here are again, we're not trying to make any claims about what RL can or can't do. We're kind of looking at what RL has done empirically, and then we're kind of making the claim that like the base models can do this on their own. This is like kind of the sharpening argument, but there's one thing of saying that the distribution is a sharpened version of the base model, and then there's another task of actually producing an algorithm that directly samples from that. So what we're doing is we're like giving an explicit algorithm that does the sharpening, which is kind of elucidating the fact that you can do a lot with the base model in and of itself without having to touch the weights. Second thing is that we kind of get access to this like richer reasoning distribution, which is, you know, we get higher performing single shot reasoning, but we also avoid this diversity collapse that RL has been documented to have. And then finally, this better base model sampling offers a recipe that's composable with reinforcement learning, as you guys have brought up, where we can not only extend performance to unverifiable domains, but we can consider like different scenarios where we use power sampling during GRPO, or like another kind of direction that's interesting is like what happens if you run reinforcement learning on the power distribution itself? Does that kind of like normalize the sharpening effect of reinforcement learning and then force RL performance to do exploration? Like it's potentially interesting to see like running GRPO using a base model of power sampling to see what happens there. And so like a final point, which is a broader outlook, I know I'm running out of time, but like kind of the general like style of work that I've been working on has kind of all been oriented around this observation that like transforming the base model distribution can elicit strong capabilities that model is not explicitly trained on. So this reasoning with LLMs was like one example. We've also done this in the diffusion space in a paper released a while ago, where you can kind of force a diffusion model to conduct these image restoration tasks, even though the diffusion model is kind of only it was only trained to generate images. So these restoration tasks are like, if I like black out most of this image and I want the diffusion model to like create an image that's consistent with this like observed non-masked region and then infill a realistic version inside, like, can you force it to do this task? And it turns out that like, again, by just shifting the distribution at inference time, you can really like coerce these models to do things that are like really just like things that it hasn't been trained on whatsoever. So like this is this in-painting region where like other approaches in the past have kind of failed to either de-blur an image or fill in this mask. But if you kind of do it the right way, then you can get these really realistic completions that are kind of remarkable to see diffusion models doing. This is kind of again, this general table. There's like two predominant tricks that you can run here. One is this annealing approach, where you take p to the alpha, which is what we did in the LLM case, and then tilting is the other approach, where you tilt by some exponential that's a function of the reward and a temperature parameter. And this is assuming that you have access to a verifiable reward to the base model. And these kind of fall into these like learning and sampling based approaches, where like in the learning case, this KL regularized RL, you can kind of construct a learning objective to try to learn the right distribution, or you can run a sampling approach and explicitly target this distribution. So KL regularized RL samples from the tilted distribution. This is kind of a somewhat folklore theoretical fact. And then like other approaches are like tilt and adjoint matching, which are separate. And then on the sampling side, there's this like Feynman-Kac steering / like sequential Monte Carlo approaches that sample from the tilted distribution. our method sampling from the annealed distribution. There's also reward guidance, which samples from the tilted distribution. But I think there's an interesting interplay between like, I think for like post-training methods, we really want to kind of interpolate between like sampling and learning approaches. There are things that we like need fundamental like learning signal on, and like sampling approaches will not save you in that regime. But I think balancing when to sample versus when to actually learn is like an important design axis that like better post-training algorithms should kind of adhere to. But yeah, thank you so much. This was done by work with my two advisors, Satan and Yilan. But yeah, thank you so much again for inviting me and listening to the presentation.
Thank you. Great work, Aayush. And are there questions online?
Sorry.
No, I say great work, great work. I was asking if there are like if people have questions online about your work, or if there are questions like in the room, except
I'm exhausted. I've lost all the chance to like answer any questions.
maybe I have a question. So when you say number of steps, right? You show the plot when you say number of MCMC steps around 10. But you also mentioned that you do this MCMC block-wise.
Yes.
So when you say, so how many times can you resample like each block?
Gotcha. Okay, yeah. So that is this equation here. So when I say number of MCMC steps, so what we're doing in this like chain of distributions is that we're running n MCMC steps from like this distribution to this distribution. Then we run n MCMC from like here to here, and like so on and so forth. So n MCMC is like 10, but it's for like the number of MCMC steps that transition between these two distributions.
So each block can be resampled around 10 times.
Yeah, each block is sampled around 10 times. So like there's a conversion rate that we did in the paper, which is like we're sampling 10 times for each block, but each block is not as long as like the full sequence. So there's like the inference cost is like, if you sum all this up, and it actually ends up being around like 8 times like a general inference, like one inference rollout. So like the total number of tokens that are expended during this entire process is about 8 times the like base process.
Do you have?
Yeah.
That's it. No, just like for each block, so you have a fixed number of times where you do the resampling, or it's adaptive?
It can be adaptive. I think there are follow-up works that tried to make it adaptive, but I think for our purposes, we just did fixed number of times and fixed number of blocks.
I see. Interesting. And one point. So when you show the plots with GRPO, related also to what we were discussing before when you were answering the question. So when you say GRPO here, this is always GRPO with like output reward, like with reward on the answer.
Yeah.
That is an interesting. I think you were discussing about different sampling regimes here, but I think one of the main reasons like methods like yours are so effective, in particular for like coverage, is that you are kind of providing a reward on the full sequence.
Yep.
You are providing like your advantage, like the MCMC ratio can be seen as a form of advantage, and you are providing on the full sequence, not only on the output. So to me, it makes a lot of sense that if you provide the reward on the full sequence, similar to like what people are doing these days with self distillation, like you provide reward on your full sequence, and even if you're using the RL algorithm, GRPO, but then your advantage is on the full sequence, you don't see this kind of collapse. That is like something very similar to what we are showing here. You provide like rejection acceptance on intermediate steps, intermediate blocks, and this implicitly it's rewarding like high likelihood or like sharpening behavior, but at the subsequence level, at the block level. Right. So I think what you were mentioning about fine tuning on these sequences for GRPO, even if you just fine tune like the model directly on these sequences, it should work quite well without the need to do full GRPO. But the main point is that I find it interesting because you are providing in a way a self-rewarding mechanism at the sequence level.
Yeah, definitely. Yeah, I will say like to that point, like one thing that we're trying right now that I've been working on is like using this power sampling as like a teacher distribution in these like self distillation or on policy distillation approaches.
Yeah.
Like to see what happens. That's
Makes perfect sense. I think this is like the right way to do it because then you can use GRPO and you reward the full sequence. You don't with your method, you don't even care about the answer. You could remove the answer and you obtain exactly the same results.
Right.
So yeah, it's very interesting.
Great.
Thanks for the presentation. Amazing work. I also have a question, and by the way, this is how. I think from my understanding, this power distribution, it works the best if if the true answer is in a mode of your probability distribution, and ideally is in a mode which has the highest distribution, because that's where you get the amplified distribution by have the alpha greater than 1 power distribution.
Right.
So I wonder if you have ever tested the case where the ground truth is not in such a mode. I think, for example, in the Pascal experiment, the figure you showed in the very beginning of your presentation, you have a llama model, llama 3 AB maybe. That model, I think the Pascal, the right side on math 500, right? So let's say even like past 128, so the success rate is still not too high. I wonder on this llama model, like how your method works.
Right. We tried on a llama variant that was easier to run GRPO on, like the Tulu methods. I think we also saw like boosts in reasoning there. I think it's not like it does outperform like what GRPO is able to get, but it's like again it outperforms what low temperature sampling is about to get. It's like between low temperature sampling and GRPO. But I think like the gap is like 2 to 3%, but it does work in these like llama style methods. But we used Tulu because it's easier to run RL on that variant because it's like fine tuned on the right data set. There's some like it's difficult to get GRPO to work on like the llama 3.1 in and of itself, but there's a way to get it to work with like the Tulu variant. But we did see like a similar boost, but it's not as exaggerated as in like the quantify cases.
Got it. Thanks. I have another question, and sorry for keeping you for another few more
No
minutes.
worries.
So I think at the end of your talk, you commented on the exponential tilting, right? And also you mentioned the connection with RL training with KL divergence regularization. I think in my mind, so that's a completely, I mean, not a completely, but very different approach than yours. For example, in your case, you don't use a reward model at all. You just amplify the base model distribution. And I think for exponential tilting, you're kind of moving the probability mass from the original distribution to like if you think about reward also as a distribution, it's kind of moving towards that distribution, right? So I wonder for those two different approaches, like which one you think which setting you think your method works better, which setting you think exponential tilting works better? Like what would you recommend?
Yeah, I think so for LLMs, I actually think exponential tilting does not work very well unless the reward is like somehow very well aligned with the base model. So like I think I'd make the argument that like when GRPO ends up like whatever final distribution GRPO ends up with, it's actually just very different from the target tilt distribution. I guess the reason for that is like with tilting you lose this like intermediate process reward, like this proxy, like how good are you doing intermediate wise. Like it's kind of hard to do this blockwise autoregressive style MCMC approach with a like exponential tilting, just because the reward is typically over the entire sequence. So the benefit of annealing is that you get this implicit process reward where like for not the full rollout, but an intermediate rollout, you can use the base model's likelihood to kind of like gauge the quality of a sequence, which ends up converting to higher accuracy downstream. For tilting, it's like extremely difficult to do this. Essentially, to do tilting right, you have to generate the full rollouts and run MCMC on the full sequence length. So I think for like language models, tilting is something that is just like really hard to do, and like the mixing time is quite long, and I think you're not actually going to get a great signal. Diffusion models are different though, because diffusion models have an inbuilt look ahead map where essentially like if you're on like a noisy like latent in the diffusion process, there's like a way to get the expected final output in like one inference call, which is not expensive whatsoever. So these tilting methods work really well for diffusion because they kind of have this implicit like look ahead map internally, but language models do not have this. So I mean, I think for language model, annealing is the way to go, unless you're able to have like a strong process reward. And then for diffusion, I think tilting works a lot better than annealing because of this inherent like look ahead process.
I really just to kind of like take on the point that I was making. Like, I mean, if I replace the power distribution density ratio that you have with essentially another model or one model, isn't that like then bypassing the issues that you're mentioning with tilting?
Like, let's say in math domain, we have like process reward
I
model.
mean, forget process reward. We can just take any other model, right? Like any other model you want to tilt towards, right? Which gives us the likelihood. And I replace the density ratio that you have with that as the target distribution. Then I think I also bypass a similar like the issues that you're mentioning. Like I think like that kind of maybe is that how you were thinking about this as well, or
Yeah, sure. Yeah, that's yeah, that was exactly my point, which is like reward tilting is like if your reward is the final like correctness, then I don't think tilting is going to work. If your reward has some like ability to give you intermediate degradations, which would be intermediate generations, which would be like using a different model's likelihood, then yeah, that bypasses the tilting issue. But it's like, I guess, yeah, the distribution that you're targeting from is not exactly the reward then, right? It's like it's some composition of like your base model and a different model that you're using. So you're kind of sampling from the joint of those two models. And I think depending on, I think you could get
one pushback would be that rewards can be written down as density ratio, right? Log density ratio of a teacher model, or like to ultimately. So I guess like I mean I'm not saying that I'm doing the mental math, but there could be a way to reduce the entire thing to an actual reward function.
Right. Yeah, that's what I was gonna say. I think this works well if you have a student teacher setup where the like student is like a distilled version of a larger teacher model. But I don't think this works well if you have like one model that's like quite large and you want to use a completely different model as like your tilting distribution. Like if you're trying to sample from a product of experts, I don't think this works that well, just because I think the reward is somewhat misaligned with your base model. But I think this would work extremely well in a student-teacher setup where you're running GRPO on a distilled version of a larger model that's like considered to be an expert or like basically perfect.
Yeah,
No.
I mean, sorry, just one last comment. So I think the reason I was curious about this tilting mechanism is because, so in my mind, this is my like kind of mental path. So you showed path K, and then I was thinking, if you have an ideal like Oracle reward model, and then path K is kind of like best of n. And then I was thinking for best of n. I think some best of n variant, you can prove somehow the optimal distribution is kind of an exponential tilting. That's why I was thinking like maybe exponential tilting work well because best of n works well. So that's kind of my mental path. But I think what you said also makes sense, especially like if it really depends on the reward model design, like how you can get signal, like extract signal from reward model. I think that also makes a lot of sense.
Okay. So in the best of like, yes, with an Oracle reward model, your point is correct. But there is also a complication that the greater K harder is to get, even if you had plus at K equal to 1, greater K harder is to select the correct sample in many cases. So if the reward model is not an Oracle, there are a lot of issues with it. I mean, not only on calibrations, just issues with like selection.
So the reward model is not ideal.
That's all.
Yes, that makes sense. Yeah.
like in the annealing approach that you're showing us, like with the CNC, we have guarantees, like in the limit. With the tilting, with a wrong reward model, we have no guarantees. We don't know what's going on.
No, we only have guarantees to converge to the power distribution. We don't have guarantees of any other sort.
Yes, yes. You guarantee you convert the tower distributions. With the tilting one, with a wrong reward model. We
No,
don't
I
know.
think like the power distribution does not have the ground truth app. Like if the sharpened is, so House first question was basically the pre-training thing. If the model did not see the ground truth, right? Then the assumption that the correct answer is in the sharpened distribution is also somewhat
Yeah, but my point is that if the reward model is not perfect, you are if the model doesn't see the ground truth, both methods would fail.
Yeah, I think he's saying the same thing.
Yeah.
I think the point is if you it's more likely to trust the reward model or to trust the ground truth is the most of your base distribution.
Okay,
This was a great talk. I
Yeah.
loved it.
let's thank the speaker again.
Thank you.
I don't think we had this much fun like in a previous talk before. So thanks for entertaining us, Aayush.
Yeah, thanks for the talk, great presentation, and thanks for answering our questions.
Yeah, of course. Thank you so much again.
Bye bye.
Bye.
Bye bye.